welcome back to the lecture series on GPU architectures and programming. So, if you remember in the last lecture we have covered these different GEM optimizations, the different ways the GEM kernel can be optimized. So, in the current lecture we will like to focus on this other ideas like how this sparse matrices are operated one. Like now, why is that an important thing? Because people have often found that this neural networks pruning them is actually useful, right? Because if you DNNs can be pruned and and the resulting matrices can be sparse, then that can actually lead to many nice sparse matrix based operations which are often found useful, right. So, several works have been proposed over these years that focus on pruning the weights of a neural network, because if you prune the weights, then that leads you to a lighter representation of the network, and that also helps you to figure out, well, there are many nice sparse matrix algorithms available, how to make good use of such algorithms, right. So, if we consider such modern pruned DNN kind of networks, right, where the weights have been pruned and you have a neural network which is represented by a sparse matrix, then such algorithms become very relevant, and some of them are also very useful for GPU style implementations, right. So, that way implementations for sparse matrix operations are beneficial very beneficial in this context, and the particular algorithm we will be talking about here is sparse matrix vector multiplication. So, you have a sparse matrix and you are multiplying it with a vector. Now, that is also an important operation that you will have to do inside the neural network, right. So, in general this sparse matrix vector multiplication in short form is known as SPMV. Now, of course, we have to understand that the very reason we want to exploit the sparsity of a matrix, that is the absence of non-trivial elements, the significant absence of non-trivial elements in a matrix is that in general, if you are storing a matrix in the memory, you are actually consuming order of n square amount of space. But if we are considering a sparse matrix where most of the entries are in general trivial or 0, then we like to use an alternate storage format where I do not incur this kind of order of n square amount of storage requirement, right. So, specifically for sparse matrices there are several such well known formats like diagonal format, LPACK format, coordinate format COO, and also compressed sparse row format CSR. So, what we will do is in this lecture we will talk specifically for the CSR format, how multiplication operation on matrices are performed using this CSR format, and how that can be optimized considering a CUDA based parallel implementation. So, this is what we will focus on. So, I will just recap. Considering the way large neural networks which we are going to really face, people perform this kind of weight pruning. Now, weight pruning will lead to a sparse matrix, and that is the reason you want to do the weight pruning, because with a sparse matrix you can have nice algorithms to work with and nice storage methods. So, one of them is the CSR storage method, which we like to introduce here, and the next thing is we like to use it for our purpose like optimizing the matrix multiplication further. So, the compressed sparse row format, it stores a sparse m cross n matrix in a row form where it uses 3 one-day arrays. So, let us call the arrays as val, col and ptr. Now, the arrays, or we will refer to them as value, column and ptr, right. The arrays val and col are of length n and z, which represents the number of non-zero values in the matrix. So, let us say inside m cross n I have got only n and z number of non-zero values and everything else is set to 0, right. So, essentially we are just interested in storing this n and z number of entries, and also we are interested in figuring out what are the locations in which these non-zero values are stored, because as we can safely say that all the other locations are just having zeros, right. Now, the col or column stores the column index and the val stores the non-zero value. So, we have one 1D array which is storing all these n and z number of non-zero values. We have another 1D array called col which is storing the column indices for each of these non-zero values, that well this non-zero value is actually positioned in this column of the sparse matrix like that, right. And then I have the other array called ptr which is storing the cumulative number of non-zero elements. So, essentially ptri will represent the total number of non-zero elements observed up till in the ith row. We will see what it means. The value of the array are derived from a recursive equation. Well, let us not get into that, rather maybe we will have a better idea by looking into an example. So, let us take this simple example. So, on the left side we have a CSR, we have a normal m cross n matrix. So, in this case as you can see the amount of storage I require is 4 cross 6. So, that is 24, and here on the right hand side I am having the storage in CSR format, and we are just using 3 1D arrays, right. So, first of all what are the number of values 1, 2, 3, 4, 5, 6, 7, 8, right. So, these are all stored in the val array, right. Now, so let us try to figure out how it can be this thing can be constructed back. Okay. So, look at the, so we will start by looking at this PTR array. So, this essentially is containing information related to the rows. Okay. Now, so I am now interested in constructing the 0th row. Okay. So, what we will do is, well, we will see that the entry for the 0th row here is 0. Now, this 0 means, well, you start looking for the entry in val 0. Okay. This means you start looking for the entry in vals 2 and so on and so forth. Then 4 means you start looking for the entry in vals 4, like this, right. So, if we just now try and construct this thing. So, for the 0th row we get that vals the 0 for PTR's 0th position I have 0. So, let us see what is this 0. This is nothing but this is the content in PTR's 0th position, right. This is the content in PTR's first position. This is the content in PTR's second position, right there. So, essentially from this, for each row I am looking into PTR and I am getting the corresponding index in val, right. So, this is essentially telling me what is the location of the first non-trivial element in that row. So, for let me take an example, for the first row I get an index 2. Now, I look into so I follow this index 2 and I look into vals 2, right. So, essentially the way what I am doing is for first row I am looking into PTR 1 and then I am looking into vals of PTR 1, that is what I am doing, right. Row 1. So, if I just write it like this, row 1 first non-trivial entry equal to vals PTR 1. Row 1's first non-trivial entry is located at vals PTR 1. In which column? In column calls PTR 1. So, for 1 you go to PTR 1. So, that is 2, right. So, you now just look into the location for 2, right, that is how it is getting done, right. So, it is here, that is the column is 30. So, I hope that is clear. So, that tells me that for row 1, so just remember this. So, for PTR's position 1 gives me some information about some element in row 1, right. So, row 0, row 1, fine. Now, then in row 1 what do we have? So, you use PTR 1's position and that since it contains 2, it tells me that the value, the first non-trivial entry in row 1 is located at this position, which is vals of PTR 1. So, whatever is the content of PTR 1, you now look into that location of vals, right. So, that contains 30. So, that means and the corresponding column position is what? So, that simply calls of PTR 1, right. So, 0 and then 1. Since PTR 1 is 2, so 0. So, columns PTR 1 that is containing 1. So, that is columns 2 that is containing 1, right. So, now I have got overall information. The overall information is the first non-trivial entry of row 1 is of value 30 and it is located in column 1 and I already know the row, right. So, this is going to be 0 and this is 30, right. Well, in that way I mean I can say that well I will be able to figure out all the non-trivial entries in the first non-trivial entries in each row, right. But what about the other entries? Well, let us first use this idea to figure out all the first non-trivial entries in each row. For example, 0. So, let us go here. So, that is 10 0, right. So, that means it is right here. Similarly, right. Similarly, for 4 you just follow it, right. So, location 4 here 0 1 2 3 4 50 and for 50 what is the column 0 1 2 3 4 2, right. So, that is here 50, right, and the last one is 8, right. So, for after 4 what do you really have? It is 7, right. So, go to 7 here 0 1 2 3 4 5 6 7, it is 80, right. So, where is 80 located? As it is saying it is in the 5th position, right. Well, there will be 2 more positions here, right, and 80 will come here in the 5th position 0 1 2 3 4 5, right. So, in that way, so this is clear because this is the last location. So, all the previous entries must be trivial, right. So, these are all trivial entries, but we know up to this, but what about the rest? Well, the rest is also easy to find. As you can see, here it is 0 and the next is 2. That means, before this in the first row I have got 2 values. Well, that means the value next to 10, so I come here to the value 10, right. The next location is telling that, well, you look into vals 2. So, that means the value previous to vals 2 is also in the first row, and the location of that, the column wise location I can just get from here, right. So, that tells me 20 is here, and then immediately after 2, what do I have? I have 4, and that takes me right here to 50, right, and for 50 I know where to go, right. So, essentially what we are following is, if you just subtract them, you know that in each row how many you really have, right. So, essentially this 2 minus 0 is telling you how many are there in the first row, 4 minus this, so that is 2. So, you have 2 elements in the second row, or the 0th row has 2 elements, the first row has 2 elements. Since the first row has 2 elements, how do you get the second element? Well, if you follow 4, you get to 50, before that you have 40, if you have followed 2, you got to 30. So, whatever is next to 30, that is 40, and it is before this one where you go from 4. So, this is also in the same row, right, that is the information. Now, of course, the location you can get right from here, which is third, right. So, here it must be a 0 and here it must be 40, and since there are only 2 elements here, so all the other locations has to be 0, right. So, I hope now it is clear that if we just keep on following this process, I can just simply keep on building the CSR format. Well, the next thing is, we will just shortly touch upon that how really this is going to help you to do. I mean, assuming that you have the storage in the CSR format, you are saving on the storage. Well, how do you really do the multiplication? Well, it's easy, right? All you need to do is, you already have the vector. All you need to do is, you have to figure out the elements in the corresponding column, right? You are just required to find out the elements located in the corresponding column, because the vector is already there. So, how do you just do it? So, you run this outer loop, you just running this outer loop. Using this outer loop, you are scanning the PTR elements, right, and then so for every I, right. So, essentially this outer loop is telling you which row to access. Now, for the regular matrix, now that row, for that you have to go where? So, suppose for any ith row, you have to start from PTR I, and how much really is this inner loop going to iterate? Well, that is easy to get, just observe our previous definition. So, all that we said was that this location 0 and this PTR 2. So, what is the difference? That is the number of elements in the 0th row. From 2 to 4, the difference, that is the number of elements in row 1. 4 to 7, that is the difference is the number of elements in row 2, like that, right. So, that is why you start from PTR I and you hop up till PTR I plus 1. How do you get the value? You just get the value in this way, that since you have set PTR I to j, you will just look into PTR val j, right, because that is the value, and the column you will just get, because you have already got PTR I's value in j, just sample from the column matrix calls j, that is giving you the column, right. And once you have got the column, you know how to get the vector values, right. So, that is how you are going to do the matrix vector multiplication by sampling these vectors corresponding location value, because this column whatever you are getting, that is also telling you which value to sample from the vector, right. I hope that is clear. So, with each new iteration, you are going to change the j, that means you are simply incrementing j, right. That means you are just proceeding through the row, right. So, you are just proceeding through the value matrix, you are going to the next element in the value matrix, because PTR has told you in value matrix at which point to start, right. So, that is val j, and then you are just incrementing following val j, right. I hope this is clear. So, if we just go back in this example, let us say you have started here from 0 you are here, then you are just following the value matrix row wise, right. So, all that you need is the start position, where to start. For example, 50, 60, 70, they are in a row, you get the idea that you have to start here. and then you are just following the elements in the value matrix, and while you follow them you are also hopping over the corresponding columns in the row matrix. I hope this is clear. So, again to just give an example, consider that this is your vector. Now, when you are hopping through this row, instead of a normal matrix multiplication where you start from here and scan through up to here, you are doing it in an optimized way. From PTR you get to val, you get 50, you get the position of 50, which would be 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, that is 2. So, you know that you have to start from here, and you know that you have to go up to this, because the position next just up to the next PTR position. So, you just scan through this. While you are scanning through, whatever you are doing is, for each of these values you also get to know what are their column indices, and then you just scan through those column indices only in the vector, because the others are not required, because they will be getting multiplied by the 0, right. So, that is how it is getting optimized. So, that I hope now this is clear. From the PTR I to PTR I plus 1, this loop is going to run. You get the starting point j in your val, you do j plus plus to skim through the val. For each of the j locations, you also know that what is the corresponding column index, and that gives you the which vector component to multiply, and that is how this CPU implementation will work. Well, how will the CUDA implementation work? Let us do a simple thing first. We will assign each thread the task of multiplying one row of the input sparse matrix with the dense vector. So, unlike the CPU implementation where we had this outer loop, now we will not have this outer loop, right, because every thread will know which row to work with, and accordingly it will just do the job. So, every thread is put in charge of multiplying one row of the input matrix with the vector. The number of blocks that will be launched will therefore be equal to m divided by the block size. So, let us say m represents the number of rows and rows of the matrix, and block size represents the block dimension that I want to use while launching, right. So, every block has got that many threads, right. So, the number of blocks will simply be m by block size, and in block size I have got that many threads. So, overall I have got this as many number of threads as there are going to be rows, right, and that is a naive implementation for the corresponding CUDA kernel. So, have a look. So, this would be my corresponding CUDA kernel. As you can see, I am writing a templatized code, because we are not trying to specify what kind of data type to be will be there for the matrix. So, this will work for any of them, right, can be float, can be int and all that. So, this is my kernel. So, since I am charging each thread to multiply one row of the matrix with a column with the vector, the dense vector. So, we will just find out the TID, the global ID of the thread, and then inside this loop we will start from TID, and we will go up to the end actually, like, or whatever is the number of threads I am going to have, right, the total number of rows, right, and then inside I have this thread that is handling all the elements of the row that have been assigned to it. So, as you can see, I am running this thread, this outer loop from TID, and I am hopping over with block dimension multiplied by grid dimension. Any idea why we are really doing it? So, let us just chalk it out. So, I want a row wise multiplication, but again let us remember this is the column measure format, right. So, the values I am really interested in, they would be like this, right. So, the thread in each of its iterations has to get values like this, I mean from which location of the matrix that I index will be found by incrementing I by block dimension multiplied by the grid dimension. As you can understand that this multiplication gives me the number of rows, right. This multiplication is going to be the number of rows of the mathematical matrix. So, I will just hop over to get to the next I like this, and then with those i's what am I doing is, once I am inside the row, I have figured out which value to get, then that thread handles all the elements of the row that have been assigned to it. So, I mean the rest of it is very simple. I mean it is similar to the CPU1 implementation. So, you start from the dptr(i). So, that is the PTR matrix position, and you are going to end of course at the dptr(i) plus 1, and for each of these locations you are sampling the column, and you are getting to you are getting what location from the vector to get, and also you are accumulating here the values and in T, and you are multiplying this vector with the val matrix corresponding location that you have in J, right. So, that is very simple, similar to the CPU implementation, right. So, in that way you are going to continue, and all you are doing is you have to figure out what is the I value from where to start in the PTR, right. So, to get to the different I values in the PTR, since you have a different representation here, you are having this outer loop. So, I hope that would be really okay with the scalar implementation. Now, what about the vector implementation? So, it is simple. Let us just optimize like this. We bring back our previous ideas of reduction. So, for each warp of 32 threads, let a warp together take care of one row in the matrix, right. So, that means we will now apply our previous reduction ideas here. So, a shared memory whose size is equal to the block dimension, that is used to launch the kernel, and it is and it is used to leverage, this shared memory is used to leverage is leveraged for storing the products of the input sparse matrix and the dense vector. So, now in some way we will use that I mean first of all, why are we really doing this? Again we are considering very large matrices, lot of rows, right, but again we also want to optimize. So, for that we want to use we want the threads to cooperate, that is why we want each warp to take care of one row of the matrix, right. And also while each warp is taking care of one row of the matrix, I want to have shared memory based partial loads, right, where the shared memory is equal to size is equal to block dimension. So, that many threads will be loading the data to the shared memory in a cooperative way. Then they will be performing partial dot products. Once the partial dot products are performed, the warp will with 32 threads will perform a row wise partial reduction. Then again I will bring some more data into the shared memory based tile for the next set of points. Again the warps will perform partial dot products and partial reduction like that, right. So, let us see how it works. So, in our CUDA vector style implementation, we get the thread ID of each block, but then I need to figure out what is the location of this thread inside the warp. So, what that let us say that my warp size is 32, 32 minus 1 gives me an array of all ones, do a bitwise AND. So, that gives me the offset, that is the thread ID in the warp. So, essentially I am getting the thread ID, I mean what is its location inside the warp. So, it is basically a modulo 32 operation I would say, right. Now, the next thing I figure out is how many warps do I have inside a block. So, I know my block dimension, I am considering I mean one dimensional blocks, right, and then I just divide the block dimension by a warp size. So, that gives me that inside one thread block how many warps do I have. Why am I really computing this? Because I want the warps to each of the warps to do the reduction for one data points, right. So, for each block I figure out how many warps are there per block, and I am really going to use this later on we will see. First we have computed this warps per block, but the issue is I want to figure out the threads inside the warp, they are going to do compute or reduction for which row, which is that is being taken care of by the next line. Well, I mean I will just like to say that these are a bit advanced, but I hope this will be clear. So, you see I have figured out the position of the thread inside the warp, then I have found that well this is the total number of total number of threads launched per block, and I am and I want to figure it out by figuring that what is the total block dimension, and I divide it by the warp size. That gives me that for each block of data how many warps do I really have, right. Now, since I have figured out how many warps I do really have, and I multiply it by the block size, that gives me how many blocks are already, I mean how many warps are already done. I mean I am only considering the current block, right. So, this multiplication gives me that, well, I mean how many warps I have already got covered by the previous blocks, and then I multiply then I add with this offset of t divided by the warp size. So, essentially what does this tell me? First of all, I have figured out, well, what is my thread, and then let us understand that since a warp of threads are going to work for a row. So, I have essentially got multiple threads working for the same row, right. So, they all are elements of the same warp, right. So, by using this formula, I am trying to figure out this in general any thread T, it is going to work for which row. That is what I am trying to figure out. So, what we really do is we have already figured out what is warps per block. You multiply it with the block ID. So, that gives me that how many warps are already done, and then you just figure out, well, you just add it with the offset, and that tells you that this current thread is going to work on this row, right. And of course, you have for each block you have got this shared tile T, which will be there for this block dimension. The next point that comes is, well, I am going to load the data from the row, right. So, for that every thread will load the corresponding data as long as this if is not less than n. So, what you get is with this row value you figure out what is the position to start from dptr row, and then from dptr row plus 1 you know what is the position to n, right. I hope this is clear. This transformation is required because every thread is not working for each row. A set of threads inside the warp are going to work for a row. So, for every thread, by doing this calculation I am figuring out for which row this is going to work, and then I am going to figure out I am going to load data from which point to which point, right. Well, once that is done, use all the threads in a warp to accumulate the multiplied elements. That is what I am going to do, right. So, first you see I have already figured out from where to start and where to end, right. Once that is done, so now from dptr I am going to do the usual calculation of multiplication from with elements from the row. So, that is what I am doing with by getting j equal to row start, that gives me the position, and from that I am getting the d vals where I have got the values in the memory, and finally I am storing it back into the sum, right. And once this is done, well, as you can see that some part we are skipping here for brevity, which is basically how the loads will be done into the vals and all that. I hope you can figure it out, but we are just talking about how the data from this input matrices d vals and they are actually going to be accumulated here, and then what you are going to do is this part, which is the important part, that is once I have these partial sums calculated, as you can see now I activate the lens. So, this is very much like the reduction optimization we taught in our reduction class, where we did reduction inside a warp, right. So, that is what you can see, that we are assigning for each thread, well, which parts of the val is going to add, right. So, once the partial multiplied values are calculated, after that all of them are written back to this shared memory, right. Now, this is where the importance of the shared memory is coming, because now I want the warp to do cooperative reduction, and of course, for that I will need the data to be in the shared memory. So, once every thread has figured out which row it is belonging to, and this is non-trivial because as we discussed earlier, a set of threads inside a warp are going to work for the same row. Once that is figured out, I just figure out what is my row start and row end, and I use them for the normal loop for doing the multiplication. After the multiplication followed by the accumulation is done, I just store back the value in the shared memory, where I will do reduction using my warps, right. And now, using these consecutive if statements, we are not getting into these details, this is something we have already covered. We are able to do the final reduction, and that gives me the final result, which is of course written back by only the thread which has the len value equal to zeros, right, because we will have one thread per warp with this value equal to 0, and that gives me the final output. So, with this we will also like to say that this is our kind of end to the coverage for the course. I hope you had a nice exposure to GPU architectures and programming, and just I will also like to thank two of my TAs who are Anirban Ghosh and Srijita Maiti. They are doing PhD in under my supervision in the Department of Computer Science, and without their cooperation and help with respect to assignments and this slide creation, this course would really not have been possible. And finally, these are the important references that are there for the last set of slides. Of course, for perceptron part, we refer to this link. For the neural networks part, and of course, there were these nice Welch Lab videos, and you can look into this recent paper called MODNN, where they discussed about optimizing the memory consumption while doing the neural network training. Now, this is really something that is useful. I mean, that is something we could not cover, but it is really useful. And there were several other sources from which we borrowed material for the convolutional neural networks, the GEM and the SPMV. So, I hope in general this was a nice exposure for you, and that would be all from our side. I thank you for attending the course.